Welcome to the Explainer. So today we're diving into a pretty wild paradox in modern software engineering. We all know AI is absolutely incredible at generating code, but here's the catch. What happens when you ask that exact same AI to review the code it just wrote? Well, usually we still get bugs. Today, we're going to break down the master blueprint for a flawless, multi-vendor AI workflow that actually guarantees bug-free software. You'd think a super smart AI could easily catch its own bugs, right? It seems totally logical. But research actually reveals a massive cognitive blind spot. You see, the internal biases and the optimization shortcuts that lead an AI model to introduce a specific bug, those are the exact same pathways that prevent it from detecting that bug during a review. They are quite literally blind to their own mistakes. So here is our roadmap for the Explainer today. We're going to cover the model inversion paradox, workspace and skill standards, deterministic agent orchestration, empirical runtime validation, and finally the 4-step master blueprint. All right, kicking things off with section 1, the model inversion paradox. To fix this blind spot we just talked about, we use a beautifully simple concept called model inversion routing. Basically, if an anthropic model wrote the code, you intentionally route the review over to an OpenAI or Google model, and vice versa. You cross the streams on purpose to break that cognitive bias. And the data backing this up is just fascinating. When reviewing pull requests authored by OpenAI's Codex, Anthropic's Claude catches about 62% of high-severity bugs. But OpenAI's own GPT 5.5, it only catches 50.5% of those exact same bugs. But here is where it gets really interesting. Flip that dynamic around. When GPT 5.5 reviews code written by Claude instead of its own, it suddenly gets a massive 9.5% boost in defect detection. This mathematical asymmetry is the model inversion disparity, and it proves that opposing models are fundamentally better at finding each other's flaws. Why does this happen? It comes down to how these models literally think. Claude allocates almost 60% of its context to a breadth-first scope phase. It acts almost like a product manager, checking for missing behavior and broad implications. GPT 5.5, on the other hand, is your deep forensic investigator. It dedicates over 82% of its context to hunting down concrete evidence and deep logic flaws. They just have completely different cognitive instincts. Moving right along to section 2, workspace and skill standards. So to keep all these different models playing nice without creating absolute chaos, it starts right at the root of your repository with a file called agents.md. This file sets the behavioral standards for the entire workspace. It enforces that model inversion rule, it mandates deterministic workflows, and crucially, it uses explicit context mode so your agents don't get bloated by reading each other's unrelated chatter. From there, engineering knowledge is packaged into portable markdown directories called agent skills. We literally route tasks to the specific models proven to be the best at them. Checking semantic intent? That goes to Gemini 3.1 Pro for its high scientific reasoning. Auditing unhandled exceptions? Route that straight to GPT 5.5. Verifying functional block coverage? That's a job for Claude Fable 5. We're effectively injecting a panel of specialized senior engineers directly into your workflow. Which perfectly tees up section 3, deterministic agent orchestration. Now, letting an AI dynamically pick which agent to call next sounds super futuristic, right? But in production, it's actually kind of a nightmare. Dynamic routing adds 200 to 500 milliseconds of latency per decision. It absolutely burns through orchestration tokens. And worst of all, it's non-deterministic. You literally cannot audit a pipeline if the execution path changes every single time you run it. The fix here is shifting away from dynamic routing to something like Microsoft Conductor. Conductor uses static YAML to define a directed acyclic graph, or a DAG. It uses local templates for routing conditions, which means it consumes 0 LLM tokens for orchestration, and it guarantees that identical inputs always trigger identical, perfectly reproducible agent sequences. Okay, let's jump into section 4, empirical runtime validation. Because look, you can have the best AI reviewers in the world reading your code, but the hard truth is that static review has a ceiling. AI tools are crazy fast at reading diffs now, sure, but a whole category of bugs will never show up in the code itself. UI rendering regressions, API failures, complex race conditions. An AI can read the code perfectly and still miss a bug that only appears when the program is actually running. That's exactly why we need systems like greptile's TRIX for your mission-critical features. Instead of just reading, the workflow dispatches specialized sub-agents into completely isolated sandboxes. They literally build the app and run the code in parallel to capture concrete evidence. We're talking pulling logs, grabbing screenshots, even capturing audio spectrograms. It actually proves the code works before the review is ever finalized.
Bringing it all together, we hit Section 5, the 4-step master blueprint.
Here is that deterministic 100% coverage blueprint in action. Step 1 is scope. This is where you bring in Claude Fable 5 to act as your senior requirement architect. You have it use its breadth-first reasoning to scan every single document in your PRD directory, mapping every feature and hardware interaction into a DAG. Step 2 is investigate, using a depth-first model to dig through traces. Step 3 is empirical execution, running that Trex runtime validation we just talked about. And finally, step 4, summarize it all into a consolidated multimodal report with hard evidence attached. Ultimately, decoupling code generation from verification isn't just throwing more bots at a pull request. As this idea highlights, AI code review is really about deciding how much deep reasoning and accountability you want structurally built into your engineering workflow. So I'll leave you with this final thought. Knowing everything we just covered today about the model inversion phenomenon and the very real cognitive blind spots of these models, are you still letting your AI review its own pull requests? It might be time to update that pipeline. Thanks for joining me on this explainer, and keep building smarter.